This conference will now be recorded.
All right, this is the videos that I promised you guys for the extra examples from 7.1 and 7.2. You have to bear with me, I might cough some, but I'm going to get this recorded for you. So what we learned in 7.1 is that we were trying to work with verifying some identities. And we were looking at this one, and I said it was one of the ones I would do on the video for you. So remember we said that when you're verifying, you don't really care about the 2u part. That's just a naming system for your angle. So what we're focused on is what can we do to secant squared of an angle minus 1 over secant squared of an angle. Now you can't just cancel out the secant squareds because there's a binomial on top. That's an illegal cancel. But remember our Pythagorean identities, we have like sine squared theta plus cosine squared theta equals 1. If we have a secant, that means somehow we divided this 1 by a cosine. So if we divide everything here by cosine squared, we can kind of get that Pythagorean identity that involves secant. So this is tangent squared theta plus 1 equals secant squared theta. If we subtract over the 1, that clearly shows us that secant squared of an angle minus 1 is the same thing as tangent squared. So our first step would be to replace that top part of that fraction with tangent squared of our angle, which is 2u. And then we have that over secant squared of 2u. This does not equal sine yet, so we need to maybe convert everything to sines and cosines. So tangent squared is sine squared over cosine squared of our angle. And secant is 1 over cosine squared. So if we take our top fraction and multiply it by the reciprocal of the bottom fraction, that will clear out those complex fractions. And that'll also clear out the cosine that we have there. So then when we clear that out, that gives us that this is equivalent to sine squared of 2u, which is what we were trying to prove on the right side. So that is that one worked out. Okay, so let's look at number 8. This one is tan squared alpha minus sine squared alpha. And you have to question, okay, so it's going to end up being a tan squared alpha and then a times sine squared alpha. So what we're curious about here is because this went from being 2 terms to 1 term, my thought is that we probably are going to somehow get this combined by converting this to sines and cosines and getting a common denominator. So if we make tan squared into sines over cosines, both of them squared, then we have sine squared alpha over 1. That's one way we could start. We could get a common denominator by timesing this by cosine squared alpha and cosine squared alpha. So that would be sine squared alpha minus sine squared alpha cosine squared alpha all over cosine squared alpha. We could factor a sine squared alpha out of the top by GCF. That would leave me with 1 minus cosine squared alpha over cosine squared alpha. And 1 minus cosine squared alpha is sine squared alpha using the Pythagorean identity again. So we're actually going to get sine squared alpha times another sine squared alpha over cosine squared alpha. Now this is really what we needed because sine over cosine is tangent, and then we would still have a sine over kind of a 1. So that's going to make this tangent squared for the first pair, because this is all multiplication now, so we can split it however we need to, and then sine squared alpha over 1, which is just sine squared. So that is that one. Okay, for number 12, this is that feature that I was telling you about, that sometimes you see like a binomial on the bottom and then it ends up on the top on the other side. So depending on how you want to work this one, you could try multiplying top and bottom by sine minus cosine and see what that gets you. Or you can try to change the cotangent and the tangents to sines and cosines. So let's try that method first. So if we do that, that's going to make this cosine theta over sine theta minus sine theta over cosine theta all over sine theta plus cosine theta. We'd want to get a common denominator on top, so you multiply this fraction by cosine over cosine. So that's sine theta cosine theta. And then we'll multiply the second fraction by sine squared, or sine theta on top and bottom, which makes that sine squared. excuse me. So that's sine theta plus cosine theta, still on the bottom. We can combine that top now into a single fraction, so that's cosine squared theta minus sine squared theta over sine theta cosine theta. And now I'm going to consider the bottom as one big fraction too, so it's all over 1 since it doesn't really have a fraction. So now we can try to multiply by the reciprocal. So that would make that cosine squared theta minus sine squared theta over sine theta cosine theta times 1 over sine theta plus cosine theta. Now, the thing I didn't do yet is this is not a Pythagorean identity because you would need cosine squared plus sine squared. But it is a difference of two perfect squares. You can factor that top. That would be cosine theta minus sine theta and cosine theta plus sine theta over sine theta cosine theta times 1 over sine theta plus cosine theta. Now the cosine theta plus sine theta, those are the same thing because the addition can be done in any order we want. So that just leaves me with cosine theta minus sine theta over sine theta cosine theta. And because the bottom is a monomial, which means no adding or subtracting, you can split this into two separate fractions. So cosine theta over sine theta cosine theta minus sine theta over sine theta cosine theta. And then we do get some reducing at this point. So this is 1 over sine theta minus 1 over cosine theta, which is two terms like we wanted for our right side, and those are the reciprocals. So that is cosecant theta minus secant theta. So it does equal the right side. Okay, we did this one in class, so we're on 16. This one is definitely, there's a binomial on the bottom and it ends up in the top for sure, and there's no other binomial there. So I'm pretty sure that this is the trick I showed you where you use the conjugate. So I'm going to try it that way. So to get rid of something using a conjugate, you multiply by the same thing that you have, but you change the sign in the middle. And what that does is that makes it FOIL to a perfect square, difference of two perfect squares. So that makes this cosecant y plus cotangent y all over, and we FOIL this out, this would be cosecant squared y. The middle terms are opposites, so they cancel, and then we get a minus cotangent squared y. Now the thing about that guy is that's a Pythagorean identity kind of in disguise. So let's go back to this. To get a cosecant, you have to divide everything by sine squared. Which gives me 1 plus cotangent squared theta equals cosecant squared theta. So if you subtract the cotangent over like our problem has, you notice that cosecant squared minus cotangent squared is just a 1. So this becomes cosecant y plus cotangent y all over 1, which is just cosecant y plus cotangent y, which is our right side. Okay, so that's the end of this one, because I believe we did all of the others in class together. On section 7.2, we had the final two problems left over that I did not get to in class, so we're going to work through those. It says find the solutions of the equation that are in the interval 0 to 2 pi, but to do that, we're going to find all possible solutions. Remember, we learned this last time, and then we'll plug in appropriate values for the angle to see how many of them are between 0 and 2 pi. So the first thing you want to consider is, can you solve this maybe? So I'm going to try to subtract the 2 over and get this cosine by itself and divide by the -8, so that's going to be 1 over 4. I will then take a square root of both sides, which makes this plus or minus the square root of 1/4, which becomes, both of those are perfect squares, so it's plus or minus 1/2. So we're solving two different equations. Either cosine t equals -1/2 or cosine t equals positive 1/2. So cosine is negative in quads 2 and 3, and for its x to be a -1/2, that means the other guy is square root of 3 over 2. So remember, that is a shorter x than a larger y, so that's 60 degrees. So this is a pi over 3, and specifically 2 pi over 3. This one would be 4 pi over 3. So 2 of my solution sets for all real numbers, not just the 0 to 2 pi, would be 2 pi over 3 plus 2 pi k, and 4 pi over 3 plus 2 pi k. Then we're going to do the same thing over here. We're going to solve this. The cosine is positive in quads 1 and 2. Same angle essentially for reference angle. So this is pi over 3 and 5 pi over 3. So t could also equal pi over 3 plus 2 pi k, or t could equal 4 pi over 3 plus, or excuse me, 5 pi over 3. Looking at my other picture, plus 2 pi k. So now you get to the point where you want to figure out what are the all of the individual solutions between 0 and 2 pi. So imagine writing your solution sets up here. So I'm going to write each one of them. And then 4 pi over 3 plus 2 pi k, and pi over 3 plus 2 pi k, and 5 pi over 3 plus 2 pi k. And you're going to imagine plugging in different values for k. Now, if we plug in k equals 0, you just get the angles. So 2 pi over 3 is definitely between 0 and 2 pi. So is 4 pi over 3. So is pi over 3. And so is 5 pi over 3. When you plug in 1, you have to realize that you're going to be adding a 2 pi to your problem. But for us, adding 2 pi is really like adding 6 pi over 3. So this is 8 pi over 3. That is over 2 pi. So that means it's not in the region 0 to 2 pi. So that one's not going to count. If we have 4 pi over 3 and we add 6 pi over 3 to it, which is 2 pi, that's 10 pi over 3. That's again over 2 pi. If we have pi over 3 and we add 2 pi to it, or 6 pi over 3, that's 7 pi over 3. That's again over 2 pi. So it looks like since we had all 4 of the pi over 3s in the normal system, anytime you add more to it, you're going to go over 2 pi. So see, none of these would be in the 0 to 2 pi range that they asked us for. So the only answers are the 4 specific ones you get from the original quadrants. Okay, so then our very last one is this one. It looks like sort of a trinomial because I see sine squared and sine to the first. Good news is they're both sines, so that means we can just start off by getting everything kind of set up like a trinomial. So I'll add the sine u back over and I'll subtract that 1 over so that everything's on this side. If you imagine letting x stand for sine u, then you can say that this is 2x squared plus x minus 1 equals 0. Factor by grouping, so 2 times negative 1 is negative 2. Factors of that are 1 and 2. If it was a negative 1 and a positive 2, that will make a positive 1 in the middle. So we split this middle into a positive 2 and a negative 1. We factor by grouping, so that would be 2x, x plus 1, minus 1 for bringing out the leading coefficient, and that would be x plus 1. So I get an x plus 1 and a 2x minus 1 equal to 0. That's either x equals negative 1 or x equals 1/2, but x, remember, was sine u. So this is asking, when does sine of u equal negative 1/2, and when does sine of u, our angle, equal positive 1/2? So for sine to equal negative 1, you have to have a y value of negative 1. That only happens down here at 3 pi over 2. So remember, this would be u equals 3 pi over 2 plus 2 pi k. And then for this one, sine is positive in quads 1 and 2. So we would look at, this is going to be a sine value where the y is 1/2 and the x is square root of 3 over 2. That's pi over 6. And that means that this would be 5 pi over 6. So we have u equals pi over 6 plus 2 pi k, and u equals 5 pi over 6 plus 2 pi k. Now again, I can go through and show you the same thing we did on number 11, where we make the chart, we plug in all the zeros, and that definitely gives me 3 pi over 2, pi over 6, and 5 pi over 6 as solutions. As soon as you plug in 1, though, you're going to go around the circle a whole time, which means you've gone past 2 pi. The only time you get extra solutions for plugging in like k equals 1 or k equals 2 is if you've had some kind of adjustment inside this angle, like a 5u or a 1/5u or something weird like that. That's the only time you're going to get extra rounds of possibilities. So it's just going to be those 3 solutions that are in this specific interval. All right, and that finishes this video, and hopefully that catches us all up, and we'll start back with 7.3 where we left off last time in class.